Now that we're kind of building towards organic molecules, we need to talk about a shorthand. Now, previous video I talked about how organic chemists really don't work with Lewis structures per se. They don't derive them every single time. They work with functional groups. Well, there's a reason for this. It's a shorthand, and you can go back with Lewis theory and show what the actual structure is, but they keep a lot of it in the back of their mind because the details aren't relevant. So if we look at something like this, we have a carboxylic acid with 5 carbons and an OH group. And this is a lot to draw. So what we're going to do, this would be a Lewis structure you draw in general chemistry. Let's talk about how you would translate this into a Lewis structure that you would draw in organic chemistry. Well, the first thing is we're going to work with a few rules that are always true for organic compounds unless we explicitly need to say if they aren't. First of all, carbon has 4 bonds to everything it makes. So if it doesn't, we'll explain why, usually through the use of lone pairs. But basically, we expect carbon to have 4 things around it, or at least 4 bonds around it. Oxygen's going to have 2 with 2 sets of lone pairs, or 4 lone pair electrons. Nitrogen's going to have 3 bonds with 2 lone pair electrons, or just 1 lone pair. Halogens only have 1 bond with 6 lone pair electrons, or 3 lone pairs. And we're just going to kind of work with those assumptions. So instead of drawing out all these carbons, because carbon appears so much, we're not going to write them in, and we're also not going to write the hydrogens. Basically, if we have a carbon with less than 4 bonds, we're going to assume the rest of the bonds are made up with hydrogen. So we have 1, 2, 3, 4, 5 carbons. We're just going to draw 2, 3, 4, a line like this. Now, each point on this represents a carbon. So this is a carbon, 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 carbon. This carbon only has 1 bond drawn between it and the carbon beside it, so we're going to assume that the remaining 4 bonds are hydrogen. This carbon already has 2 bonds, so the remaining 2 bonds are probably hydrogen. Now, oxygen we need to explicitly state, because it's a heteroatom, it's different than carbon. So anytime you don't see an atom in there, it's carbon. And we're going to have to explicitly say that it has an OH. We're not going to assume then that oxygen has hydrogen or it fills in its valency with oxygen with hydrogens, because it may not be true. We have this oxygen double bond, so we're going to write it like that. And again, we don't see an atom here. This implies that it's carbon, and we have 1, 2, 3, 4 bonds. Now, let's say we actually had a double bond there. Well, all we do is draw our second bond. And again, this carbon already has 2 bonds, so we're going to assume the remaining 2 are hydrogen, and this carbon here has 3 bonds, 1, 2, 3, the remaining bond is hydrogen. So this is where this line notation comes from, is saying that there's a lot of carbon, there's a lot of hydrogen, we can kind of fill in the gaps. Anything that isn't carbon or hydrogen, though, needs to be explicitly stated, and especially with lone pairs, we need to make sure we draw the lone pairs in there because it's going to really affect how we calculate the formal charges. Now, another thing that's typically not emphasized in general chemistry level, but does show up a lot in the organic chemistry, is the stereochemistry. So we can draw methane, CH4, like this. This doesn't give us any idea of what the relative positions are of space. Now again, keep in mind, organic chemists, this is really relevant to what gets done. We need to know the stereochemistry because the geometry in space tells us a lot about the properties of materials. So we also are going to start using the line, the wedge dash notation. So the wedge dash notation says that if we have a wedge, so the line gets bigger, the fatter part corresponds to the atom coming out of the board. The dash, the fatter part of the dash goes into the board, and it's the atom associated with being out of plane. So these 3 atoms, the H, C, and the H, are all in plane. This wedge indicates that the hydrogen has come out of the board, and this dash indicates that the hydrogen has gone into the board. And this is how we're going to represent the 3-dimensional representation. Now, you don't always see it, even though there's a geometry. And the reason why you don't always see it is that we have a compound that doesn't have chirality, meaning it doesn't have a left-handedness or rightness. There's no mirror image. Or we can rotate it to get all the different configurations without having to make or break bonds. Then we're going to leave it off. The stereochemistry is going to come up a lot when it really matters to describing what type of, if there are unique geometries associated with the molecule. So this is your crash course here on the line notation as well as the wedge and dashes.